Imagine a galaxy that, by all known laws of astrophysics, should not exist. Enormous, several times larger than the Milky Way, yet almost invisible. Not shining with billions of stars, but barely discernible, like a ghost against the backdrop of space. This is not a theory or hypothesis. This is a real object, Malin 1. Its discovery came as a surprise. For a long time, astronomers simply couldn't see it because telescopes searched for bright objects, those that create contrast against the dark background of the universe. Malin 1 creates almost no such contrast. Its light is distributed so faintly that it literally merges with the void. Only thanks to more sensitive observation methods in the late 20th century was it possible to notice the barely perceptible glow that turned out to be one of the largest spiral galaxies known. Its dimensions are staggering. The diameter is estimated at approximately 600 to 650,000 light-years, several times the size of our galaxy. Yet it has relatively few stars. This appears contradictory. Usually, the larger the galaxy, the more matter it contains and the more active star formation is. Here everything is different. The structure is enormous, but it's sparsely filled. To understand why this is strange, it's important to recall how galaxies form. At the foundation lies dark matter, an invisible substance creating a gravitational framework. Gas flows into this framework, compresses, heats up, and ultimately forms stars. This process is what makes galaxies bright. But in the case of Malin 1, gas for some reason didn't fully complete this journey. One reason may lie in the dynamics of the galaxy itself. Its disk rotates in such a way that matter doesn't have time to compress into dense regions. Gravitational instabilities that usually trigger star formation are suppressed here. As a result, gas remains diffuse and new stars almost never form. Meanwhile, a massive dark matter halo helps hold such an enormous structure together, likely far exceeding the visible part of the galaxy in mass. There's another possibility. In the past, Malin 1 experienced a weak gravitational interaction with another galaxy. Not a destructive collision, but a gentle stretching that increased its size while simultaneously diluting its matter. Such events are difficult to track billions of years later, but they can explain why the structure turned out so unusual. The most radical option, that nothing unusual happened at all. Malin 1 could have formed this way initially. If so, this means the universe allows for an alternative scenario of galaxy evolution, not bright and saturated with stars, but slow, diffuse, and almost invisible. And then a key question arises. If one such galaxy has already been discovered, how many more similar objects remain hidden? Our observations are biased toward bright structures. We see well what shines, but we barely notice what emits almost no light. This means a significant part of the universe may remain beyond our direct observation. Malin 1 changes the very approach to understanding the cosmos. It shows that giant structures can exist without brightness, without dense star clusters, and without the familiar, visual appearance of a galaxy. This is not an exception to the rules, but an indication that the rules themselves may be incomplete. If an observer found themselves inside such a galaxy, they wouldn't see the familiar picture. There would be no dense stellar disk or bright band across the sky. Space would appear almost empty, with rare stars scattered across enormous distances. From an observational standpoint, this would look more like intergalactic void than part of a giant system. This is precisely the main paradox. An object can be colossal in size and mass yet almost not manifest itself through light. This forces a reconsideration of the very principle of visibility as the primary criterion of existence in astronomy. Malin 1 is not just a rare galaxy. It's a signal that we see only part of the real picture of the universe. And the more we study such objects, the clearer it becomes. The cosmos may be far more hidden than we're accustomed to thinking. And this opens an even deeper level of reflection. Malin 1 isn't just an anomaly, it's like a window into a hidden universe. Each of its giant, nearly empty disks tells us that our picture of the cosmos is limited. We study what shines, what can be easily detected, but enormous arrays of matter, diffuse gas, dim stars, all of this remains in shadow. And this changes everything: estimates of galactic masses, distribution of matter in the universe, even understanding how large structures formed after the Big Bang. Perhaps Malin 1 is only the tip of the iceberg, and thousands, millions of similar, ghostly giants drift through space, remaining virtually invisible. Astronomers continue searching for them using more sensitive cameras, long exposure observations, and computer image processing. Each new discovery confirms the universe knows how to create not just bright forms, but completely unexpected ones. Structures where space is almost empty, and mass is concentrated not in stars but in dark matter. And if you think about it, Malin 1 changes our perception of the very nature of galaxies. We are accustomed to bright spirals, dense cores, chaotic collisions, and bursts of star formation. Here there's giant silence. Everything develops slowly, almost imperceptibly. Time flows differently here. Billions of years pass, yet the structure remains stable, not collapsing, not sparkling, not revealing itself. This forces questions that science isn't yet ready to answer precisely. How complete is our picture of the universe? How many more such giants are hidden from view? And how does their existence change our understanding of cosmic evolution, dark matter itself, and the role of interactions between galaxies? Malin 1 is more than just a giant spiral. It's a reminder that the cosmos is far more complex than we think. And the farther we look, the more we discover that the universe knows how to surprise, creating the incredible and almost invisible. It teaches us not only to seek light but to notice the shadow cast by darkness itself. And if you found yourself inside such a galaxy, you might not even realize you were in it. No bright structure around. No visual disk. Only rare stars and endless darkness. This is an almost philosophical moment, because it questions the very idea of the visible as a criterion of existence. Malin 1 exists. It's enormous. It's massive. But it almost doesn't manifest itself. And this forces one of the most uncomfortable questions in astronomy. What else exists, but remains unnoticed? And this very question makes Malin 1 so intriguing for science. It's not just an object of observation, it's a challenge to familiar models. If such giants can exist unnoticed, this means we underestimate the scale and diversity of galaxies in the universe. Perhaps thousands of such objects simply hide in the dark corners of space, and we haven't found them yet because they barely shine. This discovery also forces a reconsideration of the role of dark matter. In Malin 1, visible mass is only a small part of the overall structure. The rest is held by an invisible force. It's like a framework supporting a huge diffuse disk. And the more such galaxies are found, the clearer it becomes that dark matter plays not just a supporting role, but a central one in the formation and preservation of giant systems. Moreover, Malin 1 forces astronomers to think about time and galaxy evolution in new ways. There are almost no bursts of star formation here, almost no dramatic collisions with neighbors. Everything develops slowly, stably, and quietly. It's like a museum of the cosmos, where billions of years pass almost imperceptibly, and the structure remains stable. And the more we study Malin 1, the clearer it becomes that our methods of searching for galaxies, oriented toward bright objects, give only partial understanding. This galaxy reminds us that in the dark and almost empty regions of space, far more is hidden than we see. Perhaps the main part of the universe remains beyond our observations, and we still see only its bright shell. And this is what makes Malin 1 not just a scientific object, but a symbol of mystery. It teaches us to look deeper, to seek the hidden, to perceive the cosmos not only through light but through the darkness that forms its invisible structures. And each new step toward understanding such galaxies brings humanity closer to a more complete picture of the universe, where even almost invisible giants have their place and significance. But the most surprising thing is that Malin 1 forces a reconsideration not only of technical observation methods but of the very concept of what we consider a typical galaxy. Before its discovery, most astronomers built models based on bright, star-saturated systems where active star formation is the norm. Malin 1 shows that alternative development paths are possible in nature: colossal sizes without massive star formation, huge disks of almost empty space, and unusual gas distributions. Each new study of this galaxy gives us even more information about the role of dark matter, the influence of rare interactions with neighboring galaxies, and how galaxies can maintain stability for billions of years without dramatic events. It's like a living laboratory, revealing to scientists scenarios that were previously considered impossible. And simultaneously, Malin 1 is a warning about how limited our perception of space is. We're accustomed to judging the universe by what we see directly, but objects with low surface brightness remain out of sight. Their existence suggests that we may be seeing only the tip of the iceberg of galactic evolution. How many more hidden giants float in the dark regions of space? How much of the universe's structure can we not even imagine yet? This galaxy teaches us humility. It reminds us that even billions of years of research and the most powerful telescopes reveal only part of what actually exists. Malin 1 is proof that the cosmos is far more complex and mysterious than we imagine, and that the real picture of the universe may turn out to be far more dramatic, dark, and intriguing than the bright and familiar spiral and elliptical galaxies we're accustomed to admiring. And the more we study it, the more questions arise. How did this structure form? What processes slowed or suppressed star formation? And most importantly, how many more such silent giants are hidden in the vast expanses of the universe, remaining almost invisible yet influencing its gravitational and material architecture? Malin 1 is not just an object of science, it's an invitation to look at the cosmos differently, not only through light but through void, darkness, and invisible forces forming giant structures we're only beginning to suspect. And then another level of understanding emerges that has long eluded astronomers. The fact is that galaxies like Malin 1 can influence surrounding space far more strongly than appears at first glance. Despite their dimness, they possess enormous gravity. They can hold satellite galaxies, distort gas movement in the intergalactic medium, and participate in forming large cosmic structures, the so-called cosmic web. This means that even almost invisible objects can play a key role in the architecture of the universe. They're like hidden supports on which a huge system rests. We don't see them directly, but their influence manifests through the movement of other objects. This is why modern research increasingly focuses not only on what's visible but on how surrounding space behaves. Astronomers study rotation velocities, gravitational distortions, gas distribution. All this allows them to see what doesn't emit light. And here Malin 1 becomes a kind of benchmark. It shows that a galaxy can be giant, stable, and yet practically not participate in the familiar processes of active evolution. It's like a separate branch of development, parallel to all known types of galaxies. But there's another aspect that makes it especially important. Time. Apparently, Malin 1 has existed for billions of years with almost no changes. While many galaxies go through turbulent stages, collisions, bursts of star formation, active nuclei, here everything happens differently. Very slowly. Almost imperceptibly. This means we may be looking at an object that has preserved conditions of the early universe in a more pure form. And if so, studying such galaxies is an opportunity to look into the past. Not through reconstructions and models, but directly, through real structures that have barely changed since their formation. But the more we understand, the stronger the feeling becomes that Malin 1 is not the limit of strangeness. Because if nature allows the existence of such objects, it also allows even more unusual forms. Perhaps there are galaxies even more diffuse. Or conversely, even more massive but completely dark, with no stars at all. Objects that cannot be seen even with modern telescopes. And then the main question becomes not, what do we see, but what are we missing? Because every time technology takes a step forward, the universe seems to answer, you've only seen part of it. Malin 1 is a reminder of this. It shows that the cosmos doesn't have to be bright to be significant. Doesn't have to be noticeable to exert influence. And doesn't have to match our expectations to exist. And perhaps most importantly, it changes the direction of the search. From observing light to seeking structure. From brightness to mass. From the obvious to the hidden. Because it's there, in this almost invisible darkness, that the greater part of the real universe may be hiding. And the deeper astronomers begin to peer into objects like Malin 1, the clearer it becomes. Before us is not just a rarity, but a key to a new category of galaxies that were previously virtually not accounted for in cosmological models. One direction of modern research is connected with so-called low-surface brightness galaxies. Malin 1 is their extreme example. But as technology develops, more and more similar objects are being found, albeit smaller in size. This means the very idea of invisible galaxies is ceasing to be an exception and gradually becoming part of the overall picture. New observation methods play an especially important role here. The fact is that detecting such structures directly is very difficult. They don't stand out against the background of the sky. Therefore, scientists use indirect signs, gas movement, gravitational effects, weak brightness changes in large image areas. Sometimes data from dozens of hours of observations must be summed to see a barely noticeable galaxy outline. It's like trying to discern a shadow in darkness. Not the object itself, but its influence. And it's precisely such methods that are beginning to change astronomy. Understanding emerges that the universe may be filled with structures we simply didn't notice. Not because they're not there, but because they shine too faintly. There's another important aspect, the chemical composition of such galaxies. Since little star formation occurs in Malin 1, its gas should contain fewer heavy elements. This makes it a kind of archive of the early universe, when matter was more primitive. Studying such systems, scientists can better understand what the cosmos looked like in the early stages after the formation of the first galaxies. Additionally, a question arises about the future of such objects. Will Malin 1 remain just as diffuse and calm for billions more years? Or will it one day collide with another galaxy, triggering a violent process of star formation and completely changing its structure? If this happens, we'll see a rarest event, the transformation of an invisible galaxy into a bright one. It will be like the awakening of a giant that has been in a state of rest for billions of years. But until this happens, Malin 1 remains almost unchanged. And this makes it especially valuable for science. It shows that galaxy evolution isn't always dynamics and catastrophes. Sometimes it's stability and slow development. Sometimes, almost complete absence of changes. And this contradicts the intuitive notion of the universe as a place of constant events and collisions. In reality, a significant part of the cosmos may be surprisingly quiet. However, the strongest consequence of discovering such galaxies is the impact on cosmology as a whole. If there are many such objects, this means the distribution of mass in the universe differs from what we calculated. And this means corrections may be required in models describing the large-scale structure of space. This also affects understanding of dark matter. Perhaps it's precisely in such galaxies that its influence manifests most purely, without strong interference from stellar processes. This makes Malin 1 an ideal laboratory for studying one of the most mysterious components of the universe. But the more we learn, the more questions arise. Why do such galaxies form at all? Why does their structure remain stable? Why does almost no star formation occur in them? And the main question, are they really rare? Or have we simply begun to notice them? If the latter, this means the universe is far less bright than we're accustomed to thinking. It may be filled with giant but dim structures that form its foundation. And then the familiar picture of the cosmos, bright spirals, shining galaxy clusters, powerful flashes, becomes only a surface layer. And beneath it hides another universe. Colder, more diffuse, and far less noticeable. And that's where modern astronomy's gaze is now directed. Because perhaps it's in this hidden part of space that answers to the most fundamental questions about its nature, origin, and future are found. And as science takes a step forward, it becomes obvious, to truly understand objects like Malin 1, it's not enough to simply observe them. The very tools of thought need to be changed. For a long time, astronomy was a science of light. Everything we knew about the universe was built on analyzing radiation, visible, infrared, X-ray. But Malin 1 forces a shift in emphasis. It shows that the absence of light is also information. Sometimes even more important. That's why in recent years, methods that allow studying not radiation but gravity have been gaining increasing importance. For example, analyzing galaxy rotation curves shows how mass is distributed within them. In the case of Malin 1, these curves indicate an enormous amount of dark matter that literally dominates the entire system. This provides a unique opportunity to study dark matter in conditions where its influence is almost not masked by active star formation processes. In ordinary galaxies, bright stars, supernova flashes, and powerful radiation complicate the picture. Here, it's an almost ideal laboratory. But there's another, less obvious aspect. The galaxy's boundaries. In ordinary cases, we can more or less clearly determine where a galaxy ends, where its light ends. But Malin 1 has almost no such boundary. Its disk is so diffuse that it gradually dissolves into intergalactic space. This blurs the very concept of galaxy as a separate object. Where does it end? Where does cosmic void begin? The answer turns out not to be so obvious. And this again returns us to a broader understanding of the universe as a continuous structure, not a set of separate islands of matter. Moreover, Malin 1 gives reason to think about the role of the environment. Most active galaxies are in dense regions where interactions occur frequently. But such diffuse giants, apparently, form and are preserved in relatively quiet regions of space. This means the environment can determine a galaxy's fate no less than its own mass. If a galaxy is isolated, it can remain quiet, slowly evolving, and almost invisible. If it's in a dense cluster, collisions, deformations, and activity flashes await it. Malin 1 most likely belongs to the first type. But this raises another important question. How many such quiet zones exist in the universe? If there are many, then a significant part of galaxies develops outside the turbulent processes we most often observe. And this again changes the statistics on which our models are based. And this is where an interesting connection with future telescopes emerges. New instruments, such as supersensitive ground-based observatories and next-generation space telescopes, will be able to see even fainter structures. This means that in the coming decades, we may discover entire populations of galaxies similar to Malin 1. And then it will cease to be unique. It will become the first of many. And this is perhaps the most important moment in this entire story. Because science advances not when we find an exception, but when that exception turns into a pattern. If Malin 1 is not an anomaly but a type, then an entirely new picture of the universe opens before us. A picture where not bright and active systems dominate, but quiet, diffuse, and almost invisible giants. And then the familiar cosmos we see in photographs, with bright spirals and shining nebulae, turns out to be only a small part of reality. The rest is hidden. And it's precisely this hidden part that becomes the new object of research. Because perhaps the main mysteries of the universe are not where there's the most light, but where there's almost none. And this very idea completely changes the approach to understanding the cosmos. Malin 1 shows that the real universe may be far more vast and complex than we're accustomed to thinking. While we oriented ourselves toward bright objects, billions of quiet giants remained unnoticed. They form an invisible structure on which visible galaxies rest, and therefore exert a key influence on the evolution of the universe. Each new discovery of such objects forces a reassessment not only of the amount of matter but also of the distribution of galaxies, their dynamics, and formation history. If it was previously believed that large spiral galaxies are the standard and deviations are rare, then Malin 1 and its quiet sisters show that the very concept of a typical galaxy requires revision. The question of Malin 1's origin is especially important. What exactly formed its unique characteristics? Were these external influences, weak interactions with neighboring galaxies, gravitational shifts that stretched its disk? Or did it form initially as a diffuse giant, where gas density was insufficient for intensive star formation? The answer is still unclear, but each hypothesis opens new horizons for research. The temporal aspect must also be mentioned. Malin 1 demonstrates stability for billions of years. While other galaxies experience collisions, activity flashes, and dynamic processes, this giant preserves its structure almost unchanged. This allows astronomers to consider it a living archive of universe history, a unique opportunity to study conditions and processes that existed in the early epochs of galaxy formation. Moreover, Malin 1 forces a rethinking of dark matter's role. In ordinary bright galaxies, its influence is difficult to isolate due to stellar processes, but here dark matter practically comes to the forefront. It holds the giant diffuse structure together, preventing its disintegration. Thus, Malin 1 becomes an ideal laboratory for studying the fundamental substance of the universe, which remains one of the greatest mysteries of modern science. We must not forget that Malin 1 is a symbol of how limited our perception is. We see only light, but most of the universe's mass is invisible. Perhaps billions of such ghostly giants hide in dark regions, creating a cosmic architecture we can only guess at. And when astronomers look at Malin 1, they see not just a galaxy. They see a challenge to established models, an invitation to rethink what we considered known. It reminds us that the cosmos is far more diverse and mysterious than it seems, and that behind each discovery lie new, even more complex questions. Malin 1 teaches us to look not only at what shines but at what is almost invisible. It forces us to study void as carefully as we study bright regions, because it's in this darkness that keys to understanding the structure and evolution of the universe may be hidden. And the more we study such objects, the clearer it becomes that our familiar picture of the cosmos is only a small part of reality. In fact, the universe is far more gigantic, diffuse, and quiet than we could ever imagine. And it's in this hidden part that answers to the most fundamental questions may lie: how matter formed, how cosmic structure is built, and what actually constitutes the foundation of the universe. Malin 1 is more than a galaxy. It's a door to the unknown, a reminder that in space there are entire worlds almost completely hidden from our eyes, and that true understanding of the universe requires not only technology but also a willingness to see the invisible.